we've addressed confidence intervals and hypothesis testing for differences in the means of two populations. And, as you might have guessed, we can also address problems of statistical inference for the differences in proportions from two populations. It might be that we're not interested in the mean performance of a processor system, but we're interested in the proportion of the occurrences of a particular outcome in that processor system. For example, we might want to know whether the proportion of component parts produced outside of specifications by one machine is similar to those outside of specs by another machine, or whether the proportion of detected objects found using the current radar design differs from a new design, or whether the proportion of orders filled under a particular cycle time with one facility layout is the same as another layout. In all of those cases, we collect a sample from each population, we count the number of successes, that occurrence that we're interested in measuring, and we calculate the proportion of successes in that sample. Then we use that sample proportion to estimate the population proportion in the form of a confidence interval. We know, of course, that a sample proportion is itself a random variable, and the difference in sample proportions, p1 hat minus p2 hat, is also a random variable. The sampling distribution for p1 hat minus p2 hat has a mean p1 minus p2, and a standard deviation that is shown on the screen. Much like with previous population parameters, we use this sampling standard deviation in the calculation of confidence intervals for the difference in proportions. Note that you might encounter some textbooks that use an approximation for the standard deviation. And so we have a 1 minus alpha times 100% confidence interval within which the true difference in population proportions of the two populations really lies. We have a point estimate for the difference in proportions, p1 hat minus p2 hat. Then we add to that and subtract from it a margin of error. And as always, that margin of error is a function of variability, sample size, and confidence. For confidence, we use a z-distribution, as we assume that sample sizes are sufficiently large. Let's look at an example. Say you're a production engineer for Designs by Leslie, which produces a line of puffy shirts. There are two different stitching machines that are used for the puffy shirts, and you want to study the difference in quality of the two machines, Machine A and Machine B. Here we're going to measure quality with the proportion of defective puffy shirts. You gather a sample of 371 puffy shirts made from Machine A, and in those 371, you found 28 that had some stitching problems significant enough to consider them defective. And from Machine B, you sample 314 puffy shirts and found 14 to be defective. Let's calculate a confidence interval for the real difference in proportions of defective puffy shirts made by these two machines. If we want 90% confidence, alpha would be 0.1, and the z-value, with 0.05 in each tail, is 1.645. So the 90% confidence interval for the true difference in proportions of puffy shirt defects between Machine A and Machine B is 0.0013 to 0.0605. And we can also answer hypotheses about the differences in proportions. We might want to know if the proportion of successes in population 1 is equal to that of population 2, or are those two proportions not equal to each other. Much like before in our discussion of the differences in two means, we can rearrange these two hypotheses to have the appearance of testing for a difference, and we don't always have to test for a difference of 0. We can specify a particular difference, d0, in the hypotheses. Is the difference in proportions equal to a particular value or not? And just like always, we can address three different forms of hypotheses: strict equality versus strict inequality, greater than or equal to in the null versus strictly less than in the alternative, and less than or equal to in the null versus strictly greater than in the alternative. Equality is always in the null, with a rejection region in one or two tails governed by the statement in the alternative. The test statistic works much like you'd think it would. We have a point estimate for a difference in proportions, our sample evidence, and from that we subtract off the difference in population proportions that we'd like to determine, d0. So in the numerator, we have the difference between the sample evidence and the hypothesized value. That is, how different are these two quantities from each other? And we find that difference not in terms of raw numbers, but in terms of standard deviations. So in the denominator, we have the standard deviation of the sampling distribution. Naturally, this is a z-test statistic as we're dealing with proportions. Let's apply this test statistic to answer a set of hypotheses. Kruger Industrial Smoothing produces bearings that are used in a variety of applications. The bearing production process requires several operations to get a bearing to be the appropriate diameter. If the final bearing product has too big of a diameter, it can be repolished to reduce a small amount of excess diameter. But sometimes repolishing doesn't always work, and too much is taken off. Operators at Facility A seem to be pretty good at the repolishing operation relative to Facility B. We take a sample of 217 bearings that need to be repolished from Facility A and found that 189 of them were within specification after the repolishing operation. That would result in a sample proportion of 0.871. From Facility B, we collected a sample of 246 bearings that needed to be repolished, and 204 of those were within specifications afterward, or a sample proportion of 0.829. And say we want to know if the proportion within specification after repolishing is greater for those repolished in Facility A versus Facility B. Greater than suggests an alternative hypothesis statement, as it doesn't contain equality. We plug the sample proportions and sample sizes into the test statistic equation, and we find that Z0 is 1.27. We find the p-value associated with this one-tail test is the area above 1.27 on the z-axis, or 0.102. This is a borderline p-value. It's really close to 0.1, which would usually be the maximum value at which we'd be moderately compelled to reject the null hypothesis. For better or worse, personal feelings toward the conclusion that is being drawn by the experimenter or by the company for whom the experiment is being performed can often sway the conclusions of a hypothesis test, particularly in a case like this. Ultimately, this is a judgment call for which there is no correct answer. I'd probably conclude that the evidence wasn't strong enough to reject the null hypothesis, and that Facility A had no greater a proportion of repolished bearings within specs relative to Facility B. And this wraps up our discussion of statistical inference for the difference in proportions of two populations. We'll move on to inferences about the difference in variances.